Okay, welcome to all. In this video session, we will derive the convection matrix due to the heat generation. Okay, we already derived the convection matrix. It is AK by LE 1 minus 1 minus 1 1. Where A is the area of the element, K is the thermal conductivity, and LE is the length of the element. Okay, we also derived a convection matrix where one end it is specified with some temperature and the other end where there is a convection heat transfer. Okay, now let us derive the contribution of stiffness matrix by the heat generation. Okay, this is a body or the element where at the two ends there are specified temperatures T1 and T2, and there is a heat generation of this rate Q dash. So as at the ends the temperature is specified, the temperature is constant, the heat transfer will be from the lateral sides where the property is H, that is convection heat transfer coefficient, and atmospheric or environmental temperature is T infinity. To find the stiffness matrix due to convection, that is due to heat generation, we have considering this equation, that is integration of H into n transpose of n into ds. Why ds is here? It is surface. Okay, this is surface. In the earlier convection derivation, we have considered the ds, where it it is the along the length. Okay, now in the earlier derivation we have considered the area. Okay, the convection heat transfer, it is through the area. Now it is through the surface. So instead of dA we are considering ds, and the required property it is convection heat transfer coefficient, so it is taken H here. Okay, where nt and n are the shape function matrix, and nt is the transpose of shape function matrix. We have two shape functions, as we have two nodes n1 and n2, where n1 is x2 minus x divided by le, n2 is x minus x1 by le. Okay, substituting these shape functions, n where n is the shape function matrix and this transpose matrix. Okay, substituting these values, we have h into x2 minus, okay, these two matrices are substituted here, and the surface it is defined as p into dx, where p is the perimeter. Okay, h and p are the constant. Let us take this hp outside. So hp equal to integration of, okay, product of these two matrices. Okay, x2 minus x by le into x2 minus x by le. Similarly, x2 minus x by le into x minus x1 divided by le. So we have four terms here. We need to integrate with respect to dx. Okay, in all the terms we have denominator le square, it is common in all the terms. Let us take the le square outside. So it is hp by le square. So what it is left, you just simplify it and integrate with respect to x. Okay, it is given in detail here. X2 minus x square, so it is a minus b whole square form. So x2 square plus x square minus 2x. Okay, same thing you do it for this also, and integrate all these four terms with respect to x. Okay, the boundary conditions are applied here. The element or the body, it is varying from 0 to L. So the boundary condition at x equal to 0, it is x1 is 0, and at x equal to x2 it is L. Okay, while applying the limits you substitute x1 is 0, x2 is L. Again I am repeating, x1 is 0 and x2 is L. Okay, integrating all this with respect to x and substituting the value of x1 is 0 and x2 is L, we have this form. Okay, let us solve one. Okay, in x2 minus x whole square, it is a square plus b square minus 2ab, so it is x2 square plus x square minus 2x to x. So what is the integration of x2 square with respect to x? it is with respect to x, so x2 it is constant, so you take the x2 square outside, so the integration of any constant, it is x. Applying the limits, it is applying the upper limit, it is L, lower limit it is 0, so L minus 0 it is L, multiplied with x2 square. Applying the x2 square value, x2 is L, so it is L cube, so it is L cube. Okay, in the similar fashion you integrate x square. What is the integration of x square? It is x cube by 3. Apply the upper limit and lower limit, so it is L cube by 3. Okay, similarly 2x2 you take it outside, integration of x is x square by 2. Apply the limit, so it is L square by 2. L square by 2, this 2 and this 2 get cancelled, the value of x2 is L, so it is L cube. Okay, similar fashion you integrate and apply the boundary condition, also you apply the x1 value is 0, x2 value is L. Okay, so we have these four terms. Okay, let us make the same LCM. So you make the LCM as 6 and take the 6 outside, so it is HP by L square. All the LCM, all the denominator values are 6, so you bring it outside, so HP by L square into 6. All the values have LE cube, so LE square and LE cube get cancelled, so remaining is HPL by 6, 2 1 1 2, where H is the heat transfer coefficient, convection heat transfer coefficient, P is the perimeter, L is the length of the element. Okay, this is the matrix due to heat generation. Okay, thank you.